Good morning, folks, and good day to those folks online, wherever you may be it morning, afternoon, or evening. My name is Alan Fogwell. I'm the Chief Operating Officer for the Petroleum Technology Alliance Canada, and I'm going to be moderating the session today, which is Innovation in Advancing Technology in the Real World, an AUPRF story. Now, the first time I heard that word, AUPRF, I was very, very confused. And it's taken me a while to figure out exactly how fundamental and how important this program is. It's the Alberta Upstream Petroleum Research Fund. It's funded by industry in Alberta. But as you'll see from the presentations we have this morning, we don't just focus on Alberta in terms of advancing technologies. For example, one of the speakers today, Edom Prabhu, is from a very warm place in California, which we'd all probably appreciate today. And we've placed work in other jurisdictions all across Canada and elsewhere in the world. So this session is going to demonstrate how this fund, the Alberta Upstream Petroleum Research Fund, accelerates technology adoption for emissions reduction, de-risking early-stage technologies, and enabling pilot projects. The program has been operating under the auspices of PTAC in collaboration with the oil and gas sector since 2006 and focuses on real-world deployment of clean technologies, collaborative innovation, and best management practices. Our session today will highlight a few of these technologies and discuss strategies to overcome commercialization barriers which exist everywhere. With me today are three distinguished experts in their respective areas, all dealing with ways to mitigate methane emissions in the oil and gas sector. Our first speaker will be Tony Nafla. He's the founder and senior scientist for Equilibrium Environmental. He's an expert in risk management, toxicology, as well as investigation and remediation technologies. Second will be Edom Prabhu, who's the founder and CEO of Prabhu Energy Labs. Edom is a leader in methane mitigation and clean energy systems. And finally, our third speaker is Ian Hers, who's the founder and principal of Hers Environmental Consulting. He's a specialist in sustainability planning and regulatory compliance. So we'll first hear from Tony, then Edom, and then Ian. So Tony?
Hi, Alan. Thanks for the introduction. You can hear me?
Yes.
Can you hear me?
Yes, I can hear you. Can you hear me?
Yes, I can.
Okay, there we go.
Do you want me to share my screen or just use this one here and you'll page through?
Your presentation is up on the screen now. They'll forward it through.
All right, sounds good. Well, if we could have the next slide then. So thanks for the opportunity to present at this conference and this session. And this is a project that started in 2018. Someone had asked, can you help us out with some surface casing vent flow problems? I'm a risk assessor. I really knew nothing about it. So it's been a steep learning curve for me, but I've had some great opportunities to work with the well abandonment community in Alberta, very helpful insights, and the WIA Society, various conference attendees who've provided so much helpful information, and same with the Alberta Energy Regulator. And our funding partner who's been so helpful and instrumental really in this work is the Petroleum Technology Alliance of Canada. And we also had funding support from Husky, now Synovus. And I'd like to thank our project champion, Sean Forster. Next slide, please. So I'm going to talk about human health and ecological risk assessment. It's not a mitigation technology, but it's an optimization technology. And that's how it's been in operation around the world since the 1980s. And how we can apply it to surface casing vent flows and gas migration, and how does it integrate with regulatory policy, and then just a little bit of an example with a case study. Next slide, please. So right now what we're developing is a best practices document that will be made available to the public. and it can be applied in Alberta. It has relevance to British Columbia and Saskatchewan, and it provides a roadmap and what kind of data needs to be collected and how to do calculations to, at the end of the day, come up with a risk calculation and, in a way, a health-based guideline that can help drive decision making for surface casing vent flows. Next page, please. So as we all know, there's lots of ways that we can mitigate methane, and surface casing vent flow from the chart on the right is one of the more expensive ones. And the chart on the left shows a snapshot in time with the number of wells that are leaking within various buckets of emission rates. So less than 0.5 cubes a day, all the way up to less than 300 cubes per day. And how risk assessment kind of comes into play for helping us mitigate our greenhouse gas emission footprint is by determining which wells should be prioritized and which wells should not from a health risk point of view. And how can that help us with our inventory to manage? And so, for example, if you take one well at 100 cubes a day, that's equal to 200 wells at half a cube a day. And if we do a repair attempt and we get it from 100 cubes a day down to 0.5 cubes a day, the question here for the risk assessment is, well, is that safe to human health and the environment? And if it is, can we leave it as such and rededicate those resources towards higher leakers? And by doing so, literally expedite the rate of our emission footprint reduction for this particular type of methane emission. Next chart, please. One more. So there's a national framework for how to do risk assessment. And like I said, it started in the 1980s. It came out of the insurance industry, got transformed into human and ecological health analyses. And this is a framework that's been put forward by Health Canada. And basically, you understand your problem, you assess your exposures. So how much methane and other chemicals will people be exposed to with the surface casing vent flow? Look at the toxicology, and it's not just a methane issue. Everything's toxic. There's people who have died guzzling 7 liters of water in online challenges. So even water can be toxic. So we can combine all that information and come up with a characterization of risk. And risk assessment is a great platform for stakeholder communications, for talking about landowners and regulators, because everyone tends to be able to make some agreement that protecting human health and the environment is something we seem to all be able to agree on. It's a good baseline for communications. Next slide, please. So for surface casing vent flows within the risk assessment paradigm, it is a relatively complex undertaking, and in part because there's multiple sources of exposure and there's multiple chemicals. And it's going to be a recurring theme. It's not just a methane thing. Next slide, please. Your guidelines are a function of land use, because land use drives the receptors that can be exposed and the time through which they can be exposed. So you have different guidelines for agricultural areas, residential areas, commercial, and industrial. Next slide. And so now we look at all the different pathways of exposure. So it's not just, is methane going to leak somewhere, lead to an explosion? We're looking at exposures and chemical intake and uptake. So we're looking at transport to a house and infiltration into a house, because especially in cold climates, when we heat our houses, it creates a stack effect and you get vapor and gas migration and intrusion into a house in the same way you do for radon gas and people living near landfills and cemeteries. You can have people exposed well above ground. You can have livestock exposures, and you can have small mammal exposures. Believe it or not, that's one of our models, is assessing a burrowing mammal and the potential risk to them, because in a way they're in kind of like a confined space, although because of nature and its genius, they'll have one height of an exit hole higher than the other, and that differential height creates a differential pressure and creates airflow through the burrowing mammal habitat. So you actually have an air exchange rate, and we use that in our model. Next slide, please. So in lead up to our case study here, there's always got to be policy integration. You can take risk assessment anywhere around the world, but you have to integrate with the policy of that region and jurisdiction. So we're integrating with AER directives, we're integrating with acts in Alberta, the Environmental Protection and Enhancement Act, the Water Act, Public Health Act. and incorporating that all into the process. And then there's a number of contaminated site policy documents that actually have relevance for surface casing vent flows. And then we also look at the landfill regulation. While these aren't landfills, the contaminant of concern is similar. And so there's some useful policy there. Next slide, please. So for our case study, it was a very old well site. It's in southern Alberta, and there was multiple repair attempts done, and there was still gas migration and a surface casing vent flow. And they just couldn't get to the bubble test limit. And kind of we're running up against the barrier of what are we going to do next? And so on the spatial situation is this red cross in the middle of this diagram is where the wellhead is. It's in very close proximity to 3 buildings that are occupied throughout the day by humans. And so there's a surface cover of asphalt and concrete, which kind of caps the emissions to the atmosphere, and as a result can increase the intrusion of gas and vapor into the nearby houses. And so it was a real challenging scenario because there was high potential for risk here due to proximity. Next slide, please. So one of the things we do is we install vapor wells around the wellhead at different distances from the wellhead and also in proximity to the buildings. And one of the problems with the surface casing vent flow in the scenario of a close by building, and this would apply to, frankly, any surface casing vent flow in an agricultural area, because according to the regs, someone could build a house 5 meters away from a buried wellhead. But you have a pressurized source that's coming from the wellhead that, if leaking beneath the ground surface, would be pushing through a tortuous media. And then you have a house nearby that's depressurized. So you have a pressurized source and a depressurized receptor, and you actually have a very strong advective transport pathway that you need to consider. And part of this risk assessment is looking at what is that risk if we had a low level leaking well that we buried and we capped beneath the ground surface and it continued to emit over time. And is it safe or is it not? Next slide, please. So as part of the data collection process, you're getting soil cores and you're analyzing them for things like gas permeability under different pressures. And you can put that right into the model. And so this is an example on the left there. And so it's a function of soil texture, fracturing within the soil. And so all of this information feeds into our predictions of risk. Next slide, please. I mentioned before, it's not just a methane issue. So this is a standard gas analysis you see on the right. This was for our case study site. And you can see for C6 hydrocarbons, it's got a tiny, tiny amount of C6, 0.0055 on a mole fraction basis. However, if that's all benzene, which is a human carcinogen, even though it's present at such a small concentration, it could be the risk driver. And so this is oftentimes what shakes out in risk assessment, because you have to consider all the things that get exposed, all the ways in which things can get exposed, and all the chemicals that can create those exposures. So as part of our best practices document, people are going to have to do GCMS analysis for benzene and N-hexane and any other potent toxicant that may be present in the gas. Next slide, please. This is an example of the GCMS data that was from the site. And you always want to do background, because here there were some nearby gas stations. So you want to make sure, you're identifying source. But relative to background, what we found is in the subsoil vapor wells around the wellhead, benzene was a potential risk driver because of the concentration that was measured there, and in part because it's such a powerful toxicant. So this red highlighting is a function of both concentration and a screening value for its toxicity. And so you can do this in a risk assessment to focus and narrow your efforts on those chemicals that create or have the potential to create the greatest potential risk. Next slide, please. And this is your typical surface casing vent flow data that you get. And so, we have oxygen, nitrogen, carbon dioxide, and we also have our, ethane, butanes, and methanes present. And from a human health risk point of view, it's great that methane gets degraded to carbon dioxide in the subsurface. That's great for your greenhouse gas emission footprint, because CO2 is a less potent greenhouse gas. But from a health risk point of view, CO2 and methane, they both create risk through asphyxiation, and so does ethane, and so does propane. So we're looking at a cumulative risk from our asphyxiant gases. Next slide, please. So there's two general categories. We have these simple asphyxiant gases, and they really have a non-specific toxicological action in some respects, although they can cause anesthetic type effects beyond just their displacement of oxygen. There's some evidence of central nervous system effects. But then we have our real target tissue toxicants like benzene that affects the immune system, and toluene and ethylbenzene, central nervous system effects, and then hexane, which is a peripheral nervous system toxicant. And those have direct specific mechanisms of action, which is why they're often toxic at much lower concentrations than your asphyxiant gases. Next slide, please. And this just shows this chart is on a log basis on the y-axis, and blue is the exposure potential, which is a proxy for concentration. It's been normalized. And then the relative toxic potency is shown in orange. So something that's got a very high bar is relatively more toxic. And what you see out of all these substances is that benzene for this site blew away everything else. So it was a potential driver of toxicity. And we haven't included the modeling at this point, because it's going to get attenuated to some extent as it moves through soil and is biodegradable, et cetera. But also when you add all the asphyxiant gases together, now you have them on almost equal par in terms of potential risk as benzene. Next slide, please. And so for toxicity limits, we're not just looking at explosion. I just wanted to just get it out there that children are more sensitive. They have higher oxygen demands than adults. They're not just little adults. They have different metabolic and physiological needs. And so we're looking at that for developing our risk estimates. Next slide, please. And at the end of the day, we have a limit that's somewhere around 500 parts per million, which is very similar to the landfill gas explosive limit. So that is that 1% LEL, and a methane limit of somewhere between 330 ppm and 500 ppm would be protective of children living in a house getting exposed 24 hours a day if there happened to be a house built near a leaking surface casing vent flow. Next slide, please. Next slide. So various models, they're all really simple things. You need to know whether you're in Darcy flow or non-Darcy flow. For the case studies we've all done so far, they've all been in Darcy flow, which makes things a lot easier from the modeling point of view. Next slide. And this is, as part of the work you can do depressurization tests. So you can take one of your soil vapor wells, depressurize it, and see if you can get pressure drawdown in nearby monitoring wells. And so you start building up your conceptual understanding of the potential for gas flow under pressure at the site under a surface casing vent flow or even a gas migration situation. And this buildup test data is what people often focus on. You guys are focusing on the peak there. But what we're trying to do from the risk assessment point of view is if that, when you have your valve open on your surface casing vent flow, that is going to be your source if you cut and cap that well and put it beneath the ground surface. So we actually use that information in the risk assessment. Next slide, please. Just an example of how you get these depressurization zones around houses. There's been lots of research done on this, especially with radon and other volatile gases. It started in the 1980s down in the States. Next slide. And an example of how, as you get away from the source, we see reduced concentrations empirically, and we see reduced pressures as well. And then when you get near the house, you start getting negative pressure. So it starts pulling the methane towards it. And so basically from all of this, for this particular site, it was determined that there was a potential for unacceptable risk. And when indoor air samples were taken inside the nearby buildings, we did find elevated concentrations of not just methane, but other gases as well. And so from that, we can, start to develop our mitigative actions. Next slide. And this is just something to give you an idea of what a good rule of thumb could be for, what's in the subsurface and what's in a building. This is from contaminated site policy nationally and provincially. But basically what it is it's a distribution of the ratio of concentrations inside a building to what's right beneath the slab of a building. And as a general rule of thumb, you can use 0.01, and that's generally going to be protective. So what it means is that if you had 50,000 parts per million methane in subsoil, you could have 500 parts per million methane inside your building. And so right there, there's a decent rule of thumb for if you see more than 50,000 parts per million methane in subsurface, right away you might have a potential concern in terms of human health risk. So by assessing risks on a site-specific basis, we can help to prioritize which sites maybe would require mitigative action more quickly than others because they have greater risk profiles. And the other thing you can do is if you have a well and you've tried to get it down to a certain level, it didn't work for this case study, but there's other case studies where it does, you can reach a threshold where if you cut and cap that well below grade, you may have no adverse risk to humans or the ecology, ecological receptors. And so that would allow us to potentially rededicate those resources towards other problems because there's lots of wells in this province and other provinces that still need mitigation. And we can stop there. I think that's time.
Thank you very much, Tony. Very much appreciated. And as you can see, the industry is very concerned about surface casing vent flows and looking to find new ways to manage that challenge. Our next speaker, as I mentioned, is Edom Prabhu, who's the founder and CEO of Prabhu Energy Labs. Edom? There we go.
Hello,
Can you hear me?
everyone.
You can hear me,
I
Edom?
can hear you. Can you hear
Great.
me?
Yes, please proceed.
Okay, let's go. Sometimes when you're digging in your backyard and looking for blue potatoes, you find oil. And once in a lifetime, when you find the oil, you find it is smothered in gold. That's what happened to us. PTAC, we had an oxidation technology for making power, and then PTAC came to us and said, but will it work on lean burn engines? And we didn't know. And we found out, oh my goodness, it works really, really well on the methane slip from lean burn engines. Next slide, please. Okay, what are these lean burn engines? Gas compressor stations use large lean burn engines to move gas. And they are used because they run cooler and reduce NOx emissions. But they increase methane, VOCs, and CO. And other methods used to reduce methane and VOCs are successful. They use catalysts. Alberta gas operators have really been telling us they need a much better fix. And that here we are. Next slide. This is where we found gold. The lean burn engine exhaust had a little methane, it had a little VOCs, and it has a little carbon monoxide. When we took care of the methane, we wiped out all the VOCs, all the benzenes and the butanes and everything, and we knocked out this carbon monoxide from the engine exhaust. And rather than use catalysts, we used gradual oxidation. And to our surprise, we found that nobody else had used gradual oxidation that we can find. There are no patents on the subject anywhere. And our secret is really simple. Once it's all done, all gases oxidize in time. Methane oxidizes in the atmosphere over 10 to 20 years. If you give it enough time and enough temperature, it will oxidize. We managed to do both. And that's why we call it gradual oxidation. And we can monitor and adjust that. And we can keep the peak temperature below the formation of NOx. So you don't make NOx and you knock all the other nasties out. For the lean burn engine, it's a tailpipe bolt-on solution. You just stick it on the engine tailpipe and it oxidizes everything. In addition, at many of these compressor sites, there are other gases. Compressor packing slip. Canada has taken care of most of its pneumatic vents, but any gas that is available actually can be diverted to the oxyparator and it would also be destroyed. So it becomes somewhat of a one-size-fits-all solution for remote areas. And we have patents and we're planning to expand and get some more patents. Next. This is the results of a test we did on an engine. And this is what really blew our socks off. I knew it was going to happen, but it was still a wonderful shock when it did. The temperature coming out of the engine was 450 C, and our peak temperature was 900 C. And the methane was 4,600 ppmv. We knocked it down to 0. The VOCs went to 0. The formaldehydes went to 0, the carbon monoxide went to 0, and the NOx basically did not change. I was walking on air for 2 hours that day. Next. This is how we'd install it in a CAT 3516 engine. That's about a 1 megawatt engine. And on your left with the red lines is the reactor that shows up at 900 degrees. And at the middle is the heat exchanger or recuperator that basically raises the temperature. And if you need more detail on this, let me know. I'm happy to explain it, but I wanted to just mention that briefly. Next. Where do we stand? We are doing a demo on a CAT 3516 engine in Alberta. This is with Birchcliff, and we'll be testing in late 26 or early 27. We're targeting 10 to 15 more units in 2027. We moved to much larger CAT engines in 2028, and our pricing point is $750,000 per engine for the 1 megawatts for the 3516. And we are shortlisting qualified stainless steel fabricators in Alberta, heat exchanger folks, because there's a lot of business in manufacturing these things, and we want to put all that business in Canada, in Calgary, as a matter of fact, to the extent we can. And we also need to have establish a compressor skid and a manufacturing and testing partnership. Our plan is to make jobs in Alberta that really are good jobs, and maybe even bring in industries that don't exist if that's what it takes. So we really have scale-up potential for hundreds of manufacturing jobs. I think that's the end of it. Last slide. Thank you very much.
Thank you, Edom. That
Happy
was
to answer any questions.
we're going to hold questions until Ian is finished, and then we'll go to the whole panel as a group. Really appreciate your presentation, and there is a lot of excitement about your technology within the oil and gas sector in Western Canada. So thanks again. So, Ian, are you on the line?
Yes, I am. Can you hear
There
me?
we go. Yes, I can hear you. You can hear me?
Fantastic.
Okay,
Thank you,
please
Alan,
proceed.
for the opportunity to speak. And I want to acknowledge my co-investigator, Dr. Alan or Dr. Aaron Cahill, as well as Ian Mitchell from Millennium EMS Solutions. Next slide. Well, one of the important contexts, and really Tony alluded to this, are the large number of oil and gas wells. So our net positive past, 150 years of development, and in Canada, over 500,000 oil and gas wells. Next slide. Well, regrettably, oil and gas wells can leak, mostly methane. We know that, of course, there are other gases, as Tony went in detail on, which is really helpful context. But today I'm focusing on really the methane problem. There are lots of research studies. One of them is Trudell et al., and that researcher looked at wells in British Columbia. And the interesting thing for wells that had surface casing vent flows, most of the flows were relatively low, less than about a meter cube per day. And so that has been really the focus of our researchers, what to do with these wells with low leakage rates. Of course, we know well integrity failure and leakage is increasing in importance and visibility. And so that sort of highlighted the problem, and really, I think, has led to as well, policy that is kind of looking at what are the kind of the risks and implications of leaking oil and gas wells. The article there by Schiffner is actually quite good in terms of policy and cost of methane. Next slide, please. Well, this slide here is just a slide on sustainability approaches, and it combines the social, environmental, and economic aspects, and really focuses on the intersection of those aspects for more sustainable solutions. I like the ISO 18504 definition of sustainable remediation. It really is in application to contaminated sites, but really there are parallels. Sustainability really, touches on so many different aspects of our lives, and it looks at the net benefits, or the positive and negative impacts, and then overall what the overall kind of net benefits are with respect to environmental, social, and economic value of the work. So a balance is needed. Next slide, please. Well, this slide here is a little case study. Interesting site that Aaron worked on in Alberta with a leaking oil and gas well. A number of monitoring events were conducted to look at the emissions. So highly sensitive flux chambers can be used. And the graph on the left shows the kind of contours and the emissions, which were quite low, around 11 micromoles. And so if we look at that in terms of the emissions, in terms of carbon dioxide equivalents, that was less than 500 kilograms per year. If we then look at that well and look at the regulations in terms of requirements for permanent abandonment in Alberta and other jurisdictions, so the typical approach has been, or the general approach required, is to mitigate methane emissions. If we then look at some of these, particularly when they're remote sites, the carbon dioxide emissions involved in the site preparation, bringing heavy equipment to the site and then actually going into the well and sealing those wells, those emissions can be quite high. In this small little example case study, over 100,000 kilograms CO2 equivalent. And so there are also significant risk and impact to the environment and workers and receptors that could potentially result from the work itself. And so with this context, we'll move on to the next slide. We're really focusing on what are the solutions that can be used to mitigate methane emissions or convert the methane to carbon dioxide through oxidation. This study was by Dr. Cahill, and it's in the context of natural methane oxidation in the subsurface. And the conclusion was from the study that those can be quite significant. Next slide, please. Really then, what we're looking at is how can we improve on this through engineered passive biocover or biocell technologies. So the challenge and the opportunity are solutions for oil and gas wells with low gas leakage rates. The context, as I explained, reabandonment can be costly and is often not sustainable. We really felt that alternate solutions are needed for integrity compromised wells with low leakage rates. So we think methane oxidation is a very promising contender. So if we look at the emissions over 20 years, it's up to 97% lower. When we look at full oxidation to CO2, but it's not magic. It's fairly complicated with multiple factors affecting rates. Nonetheless, we think it's the most promising alternative management strategy. Now, to really demonstrate this technology, we felt that we needed demonstration projects. There is extensive research kind of at the theoretical or laboratory scale. So lots of good work is being done. We know that methane oxidation in soils is a very well-known process. It's being demonstrated again in the lab in column studies, but we needed to take it to the field. Just in terms of the schematic there, that shows the methane oxidation to carbon dioxide, and heat is also produced, which is an interesting byproduct. Next slide, please. Well, the first phase of our project was a controlled methane injection biocell demonstration project. It was conducted over the last several years. It was completed in fall of 2024. We constructed a biocell. We looked very closely at different bioactive medias. We settled on a compost and wood chip mixture. We conducted baseline monitoring and then injected into that biocell. We had continuous monitoring, a number of parameters, gas flux, temperature, moisture. We also had discrete monitorings, things like composition and isotopic analysis. Of course, we looked at the microbes and soil properties. So extensive data set, thousands of data points. This is, of course, in the context of a demonstration project. Our ultimate goal is to develop a technology that can be readily implemented in the field at remote sites without the monitoring that has been conducted here. Next slide, please. Here's our biocell construction, an insulated box. We have a gravel layer for gas distribution. We have extensive soil gas monitoring, flux chambers, and a gas injection system. Next slide, please. Here are some key data. We have extensive data that I could have showed you. This is just one of the plots of continuous flux chamber monitoring conducted in October of 2024. It shows essentially no methane coming out of the cell. We had a very slight blip there, but overall the net emissions were very low. So that biocell at that period of time essentially degraded all of the methane that was being injected. We did notice, I haven't shown the data here, is that the performance did decrease when temperatures plummeted in late November. And then at that point, we had to stop that study. And we were really left with the question is like, what would the 4-season performance be? And how could we optimize performance of these cells? So let's move on to the next slide. Well, here's the next phase of the study, which we're really super excited about. Here's where we're taking this concept, which was demonstrated at the injection scale to a remote site. Really, a field trial and expansion of the application is needed to demonstrate the solution. Our key objectives are 4-season data, improve microbial understanding, and cost and performance data. So we have a site now that's in Alberta where we're constructing this biocell. Next slide, please. Before I get on to a few photos of our recently installed cell, I did want to touch on the amazing world of microbes and the power of analysis. We'll start with the power of analysis first. Over the last decade or two, there's been absolutely amazing advances in microbial analysis. So probably, as we all know, there's metagenomic type sequencing of the genome. In some cases, it's referred to as shotgun sequencing, meaning that it can be quite broad and really tell you what's there down to the genus level. This happens to be a study that was conducted by someone else with column studies looking at methane oxidation. We're planning some very similar type testing. And then just the extensive research that has been really interesting. The methanotrophs are highly efficient and act over a large temperature range. Different bacteria dominate depending on temperature. Cool temperatures, there's Methylobacter psychrophilus. Hot temperatures greater than 30 degrees, there's Methylocaldum. The optimal temperatures appear to be around 30 degrees. Biodegradation certainly slows down at low temperatures. And so this really has led us to kind of look at, how do we optimize the design for temperature and methanotrophy, possibly even seeding. So let's move on to the next slide. So really, again, we're looking at cold weather performance data is needed. One of the things I mentioned about the oxidation process, it produces heat. The self-heating is advantageous, particularly if we can design the cell to contain that heat. Next slide, please. I think that this slide here is probably just data intensive. It shows photographs of the installation. Would it be possible for me to share my screen, or?
Actually, Ian, I don't think we have the time right now. We're almost out of time. So was there any particular point that you wanted to mention about that particular slide?
It is a photograph of our biocell being installed at our field site. And it's just a beautiful photograph of the fall Alberta landscape, farm field with a well. And there is this cell. The next steps are to hook that cell up to the well and to start monitoring. And so we're at that stage of where we're getting close to collecting 4-season data, again, which we're really excited about. So,
well, thank you very much, Ian. And if we can have all the presenters on the screen at the same time, please. All right, folks, we're almost out of time, and therefore we don't really have time for questions. I'm going to give each of the speakers 1 minute to give everyone their key message, their key headline of the work that you've done with the support of the AUPRF program. So we'll start with Tony. What are your key points that you'd like to leave with the group?
Key points are, as Ian highlighted even more wells that we got to be paying attention to. And it's like, we got to be thinking about future generations here. We got to be really smart with our resources and how we approach these sites. both from a management point, a guideline point, and a remediation point, and how future wells are completed. And so my key point is this PTAC project is going to have the ability to provide a platform to really improve our efficiencies and optimize which wells and how hard we chase. And hopefully we can make a big dent in these so we don't leave this as a boondoggle of a legacy for future generations.
Thank you, Tony. Edom, any last
If
words?
you can, if you can oxidize weak gas, you can oxidize any gas. All you have to do is dilute it. If you oxidize methane, you can oxidize any other hydrocarbon. They all oxidize at lower temperatures. So it's a very simple solution. It takes no catalyst. All we have to do in the beginning is heat up our chamber, and then it's self-sustaining. And we can make power as well. Because if you can oxidize weak gas, you can oxidize stronger gas, and you can make power, and you can make power with zero emissions.
Thank you. Thank you. And Ian, please.
Well, I'll build on that in terms of just the subsurface. Just the microbes are incredibly efficient in oxidizing methane. And really, what we're trying to do is to optimize that process to make those microbes happy in terms of their environment. And there are ways to do that and to really come up with a passive solution that is going to, I think, improve the overall management. So, that's the bigger, I think, part is like, how do we develop technologies to improve the way that we manage larger portfolios of wells with solutions that are adaptable and implementable in the real world. Remote sites, challenges with cold, obviously winters in the Canadian north, and that's what we're really, I think, excited about is coming up with these solutions, taking them from kind of where we know that they work well in the lab, in theory, to practical application in the field.
Thank you very much,
Alan,
Ian. Sorry,
Alan,
go
I have
ahead,
to say,
Ian.
you are impeccably dressed. I am impressed.
Thank you, Eden.
Yeah,
I'll tell my
I'll
mom.
second that one. I noticed that right away too. It's looking really sharp.
Yeah.
Gentlemen, it's always a pleasure working with you, and you're just a few of the many people we work with in the AUPRF program. It's a real joy to be exploring these innovations and advancements in technologies and processes, and you make it a pleasure to come to work every day. Thank you very much.
Thank you.
Thank you, Alan.
Thank you.
Thank you. That ends our session, and the next session will be starting shortly. Thank you.